Let's talk graphs and domains now. For the graph of a two-variable function, let's check this out for a second. Right, the graph of a function of two variables consists of all the points x, y, and z that are described by the function. This graph is often a surface denoted as S, so we can see we call them surfaces in 3 dimensions. The domain of a two-variable function is the set of x, y points. So here is the domain. Notice it is a two-dimensional graph. So this is our 3D surface of our original function. This is our 2D domain. Notice it is on the XY plane, right? So 2D, this is our domain on XY plane. Because remember, when we are dealing with these multivariable functions, z is our outputs, not y anymore. So that's going to be a part of our range, which we're not going to talk too much about range here because it's actually a lot more difficult to find range for these types of functions. So we're going to deal with domain, which is challenging in itself, right? So we're going to look for the set of x, y points that satisfy what we need for our inputs, and they're going to live on this xy plane, or this xy graph. Sorry, that is xy, right? And so this is where our domain lives. This requires some knowledge of graphing, and so this is our 2D. For our graphs, we are going to utilize technology. Graphing these by hand is just extremely challenging and kind of really not worth the time. However, we would like you to explore them just a little bit. We will not need to learn how to graph these by hand. We will use technology to draw these surfaces in 3D space. If I do have you do some any homework problems or deal with any 3D graphs, I do want you to use these 3D graphing calculators. I do have a preference. I am a fan of what's called CalcPlot 3D. You can in fact just Google it. I have linked it on the homework. I do want to show you, here are some great ones also. However, they can be somewhat limiting in their ability to use them. And so I did want to show you, you can play with the ones that you like. Again, I've linked some options on the homework. Let's take a look at what these graphs look like. So what I did was I went ahead and graphed the functions that you guys see on your page. Give it a second. And I have already typed them into my function. So here is the first one. We can zoom in and zoom out using these buttons. Let's zoom out just a little bit. So here's the first one. Z equal to 2. Right? What z equal to do, it's just a plane. Again, like a little slice of paper where x and y can be anything, but my z value, you can see those labels on those x-axes, is 2. For the second one, f of x, y equal to x plus y plus 2. It is also a plane. It's kind of like a sideways plane, right? Technology does a really great job of doing the work we don't want to do. We can turn them around and help visualize them. We can mess with these windows all we want. But that next one is a plane. For the third one, f of x, y equal to x squared plus y squared. We get this shape. So it's kind of like it's like a parabola, except now it's like a bowl, right? You can kind of see that. You got the positive z-axis in there, right in the center of that bowl. This is called a paraboloid, is what this is called. Again, right, just utilizing technology here to be able to graph these three surfaces. So I'll have you guys explore that. Let's talk domain. This will be the longest video, longest chat we are going to have about domain. We are going to have to keep some things in mind, and that is what we know about some previous functions, right? Like rational functions. We can kind of see this one right here, g of x, y, it's got that rational look. I remember when we were dealing with rationals, we just wanted no division by 0 when we're talking about domains. So those same ideas are going to stand true in this discussion. So let's look at this first one. This first one kind of's got that polynomial look that we're used to seeing, except now we've got 2 variables, right? So I would say like looks like a polynomial. This one, you've got that square root function. Remember, the only thing you don't want is to take the square root of a negative number. So we don't want a negative number inside. And then for our log functions, it's been a while since we've dealt with them. As a reminder, with log functions or the natural log like this one here, we just don't want the inside to be negative numbers, right? So don't want negative numbers or 0 inside the log, right? We don't want it in here. Okay, so we're going to use these facts to help us determine the domain. It is a little funky. These are going to be definitely very newer to us, right? And so when we are dealing with the function with 2 independent variables, right, the domain still is a rule that assigns to each ordered pair some xy inside the domain, and then we get an output, which we found is a real number, right? And so as a function of a single variable, it's important to understand the set of inputs for which a function is defined, right? And we kind of talked about that across the board, kind of looking at these just using our previous knowledge, right? Where the domain is the set of all inputs, right? And so there's a little bit of a notation we can. Before we were dealing with real numbers. Now we're dealing with real numbers in 2 dimensions. So this is where this R2 comes from, right? You can think of this as all real numbers in 2 dimensions, right? And an example of R2 is your XY plane, right? A little bit more notation, 2 copy. R3 represents all the ordered triples, right? So you can think of that as all real numbers in 3 dimensions, or we call it 3 space sometimes. But let's go through these. Let's do the polynomial first, because the polynomials in multivariable cases is the same for in terms of the domain as it is for a single variable. Remember, the domain of all polynomials before was all real numbers. And that's going to stay true, right? Except now we are in 2 space, so we want R2, right? So basically, when we're looking at this function, x and y, we can plug in anything. So they can be anything. It is common that when we are working with these, we are going to be creating a relationship between x and y, both algebraically and through a graph. And so I am going to draw the graph for this one. It is going to require some shading, so I'm going to bust out my highlighter because the domain is this entire plane. So we're going to highlight everything that works, right? And so the relationship in terms of the domain that we have is R2 and the graph down here. Those are going to be our solutions. All right, let's move on to the square root. What we've talked about is we just don't want the inside to be negative. So 9 minus x squared minus y squared just needs to be positive. It can in fact be equal to 0. So that works out. For this one, we're going to have to develop a relationship, one that we haven't worked a lot with. I'm going to add x squared and y squared to both sides. So I want 9 to be bigger than or equal to x squared plus y squared. So this is what I'm talking about right here. This is our current domain right here, algebraically, right? And if you need help graphing, definitely look this stuff online, right? But this is, in fact, a circle with radius 3. I got that from the 9. You just take the square root of it and it'll give you this radius, right? Because the definition of a circle looks something like this. X squared plus y squared equals r squared, right? So 9 is 3 squared. That's where I got my r value from. And so there's the domain algebraically, a little relationship between x and y. But I am going to draw a graph, which means I'm going to get that circle on there. Again, use a graphing calculator to help you. Here's my xy plane. I'm going to draw my circle centered at the origin with a radius of 3, right? There's my center. And the idea here is, like with the last one, we had to do a little bit of shading with our highlighter. And it's like, where do we shade for this one? Am I going to shade in here? Am I going to shade out here? Like, what is that going to look like? And so what I like to do is pick a couple of test values, right? Because the question is where do we shade? Where do we shade, right? And you know me, when I pick my test values, I'm really nice to myself. I'm going to pick the point 0, 0, that center point. That just tells me, am I going to shade in the inside? Am I going to shade on the outside? Talk a little bit about this circle in just a minute, but let's test it out, right? So I have 9. Is it greater than or equal to 0 squared plus 0 squared, right? 9 is in fact greater than 0 squared plus 0 squared is just 0, right? And so for the test values, the idea here is this true or false? Is 9 greater than or equal to 0? Well, yeah, it is. So this is true. So this tells me that I'm going to shade in the center. This is definitely a big jump from what we've thought about domains before. Should we pick another value, right? So this told me shade here. Shade where the point 0, 0 is what that told me. So let's say I pick the point, I don't know, something that's not in the shaded region, just to kind of convince you, like the point, let's say 4, 0. Right? So is 9 bigger than or equal to 4 squared plus 0 squared? So 9 greater than or equal to 4 squared is 16. And look at false. Right? So what that's a point right over here. What that's saying is don't shade here. And so the idea behind, like, only needed to, you had like 2 spaces to choose from. You had to choose between inside the circle and outside the circle, thanks to continuity. If I pick a point here, it relates all the points outside the circle. Again, same idea with inside. Continuity means we'd only need to test one value, and it's going to give us information about everything inside that circle. Now I want to talk a little bit about what's happening on the circle. So this circle, the way that I drew it was very intentional. Let's compare it with the next example and we'll revisit this idea. But there's a reason why I used a solid line. Okay, so let's look at this x squared minus y squared. Said it looks like a rational. Can't divide by 0, right? So x squared minus y squared just can't be 0. So we're trying to develop this relationship with x and y. We don't have interval notation anymore. We just have these graphs and these like functions that I'm building. I'm going to add y squared to both sides. So I just don't want x squared to equal y squared. Well, where does that happen? The only places where, I mean, you could solve this, right? You would get plus or minus x cannot equal plus or minus y. assuming that I take the square root. So what you have is you don't want x to equal negative y. You don't want x to equal positive y. And so where we're going to draw this graph is where all the x and y values are equal. But notice something a little different I'm going to do. Bear with me for a second. The line that I'm drawing right here is where x equals y, right? So like the point 0, 0. This is the point 1, 1, 2, 2, 3, 3, where all the x and y values are the same. But because since we're squaring them, we need to consider the negative values also. So this is where we see points like, we'll label one of them, negative 1, 1. Right? Where all the values are the same regardless of sign. Right? So like, again, like this point was 3, 3. Let's say. So same value regardless of sign. Okay, so the reason I used a dashed line for this one here is because these are the values are not included, right? We don't want to include these. That's what dashed means. Don't include, not included. For this one, the reason I used a solid line was because if you look closely at the inequality, there was an equal to portion. The equal to portion, I can be equal to 0, right? So anywhere along this circle, equal to, right? Included in the domain. All right, so let's write that. Dashed line means don't include in my graph. However, all these other values, and you can pick some test values and you can see, as long as x and y aren't the same number, when you square them, they're not going to be equal, right? So this whole shaded region is definitely going to be included in my domain. It's just everywhere along those dashed lines is what we don't want, where x and y are the same number, whether it's positive or negative, right? Because we're squaring them. So in terms of domain, you've got the graph, and you've got this like relationship where x squared cannot equal y squared, right? So we got both of those things. For the natural log, right? We just don't want the inside to be 0 or negative. So I'm going to set the inside to be greater than 0. No equal to portion here like we had with this last one. So we'll have some dashed lines, right? I like to make a habit of kind of like solving for y if I can. And so I'm going to add y, or like getting them on different sides, or trying to create formulas that are familiar to me. So we have a relationship between x and y. What I just want, as I kind of compare this to the line, I just kind of changed the order, y equal to 4x, right? Where I have a slope of 4 and a y-intercept of 0. So that's going to help me with my graphing. Again, you can use a graphing calculator on this particular assignment to help you decide. Right? And so I want a y-intercept of 0, which is right here. I need a slope of 4, so I'm going to go up 4. 1, 2, 3, 4 over 1 and get that point right there. But since we don't have an equal to portion, we are going to draw this with a dashed line, meaning I don't want any values along that line to be a part of my graph. Now, the options are, is am I going to shade here or am I going to shade here, right? And so I'm going to pick a test value. I have one part of my domain ready to go right here. Now I just need to put together the graph. And so I'm going to pick a point that is kind to me, like this point maybe right here, the point 1, 0. I'm going to plug it into that relationship, 4 times 1 greater than 0, and I'm going to ask myself, is this true or false? So 4 times 1 is just 4. Is 4 bigger than 0? True. Right? So that tells me shade over there. Shade where 1, 0 is. Thanks to continuity, I get to shade the whole area. Well, as far as I can shade and stuff. I mean, you can play around with different values and you can kind of convince yourself should you want to. But let's say I tested another value, like the point, let's do this one right here. That's the point 0, 1, right? So 4 times 0 bigger than 1. Is 0 bigger than 1? False, right? Don't shade there. So that was this point right here. We got a false statement. That means don't shade over here. These values are not a part of my domain.